floor. Here's the information we're given and asked for. 8 foot by 16 foot rug is equivalent to 80%. The room is 16 feet long. How much wider must the rug be to cover the whole floor? Summarizing, this is what we're given. This is what we're asked for. We can make a diagram now because we can think specifically about rugs and rooms, and it's not very abstract. There's the rug in the gnarly looking rug fabric kind of part of the diagram. The bare floor is green. We want to know how much is sticking out. We can say, all right, we're given the percent, we're given the part, which is the 8 foot by 16 foot rug. What we want to really know depends on the whole. What's that whole, what's the square footage of that whole room? Because we're talking about covering, we're really going to have to work with area. What's the actual area of the rug versus the area of the room? The area of the rug, it's a rectangle, it's the length times the width. 8 by 16 is 128 square feet. That's 8/10 of the total. So the 0.8 times n, where n is the area of the whole room, is equal to 128. 80% of what number is 128? To get n by itself, we divide both sides of that equation by the 0.8, which represents the 80%. When we do that, dividing both sides by 0.8, we find that n is equal to 160 square feet. The area of the rug is 128 square feet. The area of the whole room is 160 square feet. We know one dimension of the room. The length is 16. 16 feet times the width of the whole room is 160. We can divide both sides of that equation by 16, but almost by observation, 16 times what gives 160? If you were to do the division, you would get that the width of the room itself is 10 feet. We can now modify the diagram to this. The width of the rug is 8 feet. The width of the whole room is 10 feet. What is the difference? We obviously, when you hear the word difference, subtract and find that the extra width of the rug, we need to add 2 more feet to the rug to cover the whole floor. A question might be, how can we check something like this? Well, is 128 feet of 160 feet equivalent to 80%? In other words, let's work backwards. We got 160 by calculation. 128 over 160 is 0.8 or 0.80, which is equivalent to 80%. Having taken the 160 I derived, working backwards to something I'm given, gives me confidence that my answer is correct. Another type of portion problem is a commission, and that's a portion of the sales earned that a salesperson receives. For example, in real estate, if I sold a house for $100,000 as a real estate agent, I would get a percentage of what that house is sold for as a commission. Car dealers or car salespeople also often get commissions on what they sell, and that brings us to the problem. Slick Sam, the used car salesman, earns a commission of 17%. If he manages to unload the Edsel for $4,500, how much does he earn? Here's the information. He earns a commission of 17%. The price of the Edsel is $4,500, and we want to know how much he gets of that selling price. If we summarize, there's the information we're given, the cost, the whole thing, the commission 17%, and we'd like to know what piece of that $4,500 does Sam earn. There's a diagram, and we like to know what that one slice of the pie is, the 17%. There's the whole, there's the percent, and here's the part. We can work with those three things. We know that the whole times the percent will give us the part. What is 17% of 4,500? What x is equals 17%, 0.17 of 4,500? It translates almost exactly. If we do the math here, we find that x is equal to 765, and answering the problem, we say that Slick Sam earned $765 of commission by selling the Edsel. Good for him. And we can check, of course, we can say, is 765 17% of 4,500? In other words, turn the problem around. 765 over 4,500, we do that implied division, we get 0.17, which is equivalent to 17%. Having run the problem backwards, I'm fairly confident that it's been answered correctly. Another thing we studied was percent of increase or decrease. How does something get bigger over time or smaller? And how can we put numbers on that? Let's look at an example. As I was nosing around the internet, so to speak, I came across a list of endangered species. And one of them was the Arizona ridge-nosed rattlesnake. And I just put some numbers in. These may or may not be very accurate, but it will enable us to do this problem. 20 years ago, there were perhaps 7,500 of these snakes. Now there are maybe 2,500. What we'd like to know is, what's the percent of decrease? In other words, they went from 7,500 to 2,500. Here's the information. We originally had 7,500. It's down to 2,500. We want the percent of decrease. We're given the original number and the present number. It's decreased, not increased, and we're asked what the percent of decrease is. We can put together a diagram like that, and we'd like to know what that percent is. Using the original definition, the percent decrease is equal to the amount of the decrease over the initial amount times 100%. The first thing we need to calculate is what actually is the amount of the decrease. It's not the 2,500. It's actually the difference between what you start with and what you have when you're done. So the amount of the decrease here is 5,000. 7,500 minus 2,500. Now we plug this into the formula and do the math. 5,000 over 7,500 gives me 0.66666666666. In other words, it keeps going forever. That's why that little line is over the sixes. And I'll round that off to a 67% decrease. Because, again, when you talk about the amount of the decrease, you don't talk about the final amount. You need to understand the amount of the decrease is actually the difference between the amount you start with and the amount you finish with, and you divide that by the initial amount. The same goes for the amount of increase. Suppose these rattlesnakes were tremendously prolific, and then because they're protected, they increase over time. The percent of increase would be the amount of the increase. Maybe they went from 2,500 to 8,000. So the amount of the increase would be the difference between 8,000 and 2,500. So you always have to subtract the endpoints to get that change. It's not one or the other of the endpoints, it's actually the change. And that's the important thing to remember in doing these percent of increase or decrease problems. Let's check our answer. What is 67% of 7,500? If I work that out, 67% of 7,500 in fact is 5,000, which is the amount of the decrease, the 7,500 minus the 2,500. Because this works out, I'm going to say that we did this problem correctly. Let's look now at a discount problem which also involves percents. Here's one, and a relatively simple example. Some boots are on sale, and this is actually a picture that I scanned from the newspaper, so this is true. Some $69.99 boots are on sale for $39. What's the percent of discount? It's always $69.99. Why couldn't they make it $70? Oh, well, we all know. Let's summarize the information. We have $69.99. They're sold for $39. What's the percent of the discount? And in a way, this is a percent of decrease problem, because when something is discounted, it's decreased. The same as when you add tax to it, you can look at that as a percent of increase. Here's the information. We start with $69.99. The discounted price is $39, and we're asked for the percent of the discount, which is also a percent of decrease. We can do exactly the same kind of a diagram. There is the total amount, the discounted price, and the amount that's left over that we're looking for. The discount, remember, is the marked price, the original price minus the sale price. Similar to the decrease is the initial quantity you had minus the final quantity you had. This works the same way as a percent of decrease problem. The discount price, you remember, is the marked price, the original price, minus the sale price. In other words, it's the difference between the original and the final. Very similar to our snake problem. If you think about it, we had the 7,500 snakes minus the 2,500 snakes. Here we have if we put the numbers in, we had the original price, which was $69.99, minus the $39. That's the discount, and it's equivalent to the decrease, if you want to think about it as an equivalent thing. When we do the subtraction, we get that the discount, the decrease, is $30.99. We also have another piece of information. We know that the discount is given as the rate of decrease, the percent of decrease, the percent of the sale, times the marked price, the original price. That $30.99 then is equal to the rate, the discount percentage that we're looking for, times the $69.99. How do we get the rate by itself? We divide both sides by $69.99, and that gives us the rate equal to, if we do the math, 0.443, or this is effectively a 44.3% discount for this problem. To check the problem, we work it backwards. We ask, is 44.3% of $69.99 equal to the discount? We run that backwards. If we do this multiplication, we get $30.99, and in fact, we're okay here. Discount problems are nothing more than finding the percent of decrease. You start with something, you wind up with something less, it's decreased, how much is it? Let's look at another one of these. It seems that shoes are wonderful because I can always find examples in the newspaper. Final clearance, shoes, total savings, 73%. Let's zoom in on those total savings and ask are they being honest with us? It looks like they probably might be. If I'm starting with $59.99 and winding up with $16, maybe that is going to be a total savings of about 73%. It's a little bit confused because they get it down to the $59.99 to $20. then it's whatever it is, they take off another 4, but we're going to look at the final value, starting at $59.99, there's that 99 again, ending with 16, and try to calculate what the percentage of savings is. Let's see what we're given here. The marked price is $59.99. The sale price is $16. What we're actually asking is, what is the sale price if, in fact, we're given a discount of the 73% that they claim we're given? There's the $59.99. There's the 73%. And is that really $16? Is the discounted price really $16? By definition, the discount is the marked price, the original price minus the sale price. I put a little 1 beside it because I'm going to calculate the discount 2 different ways given the information we got, then compare them. Let's look at it this way. That discount is $59.99 minus $16. If I do that subtraction, I find that the marked price minus the sale price is $43.99. I also remember another definition of the discount if I know the discount rate, and I'm going to call that discount 2. That's the rate times the marked price. Remember, they gave us a rate. They told us that the rate is 73%. I'm going to multiply the 73% times the $59.99 and see how it compares to getting the discount by doing the subtraction. When I do the math, I look at this and I see that there is a very small difference, 20 cents or so, and it looks like if you calculate it the first way, it's a little bit bigger than the second way, but given everything, I would say that they're more or less telling the truth. So when we ask the question, is this the truth? The answer, if you know math, is yeah, pretty close to the truth. Speaking of whether or not something is correct, let's talk about truth in lending and look at some interest problems. Here's one. Jay borrowed $3,000 from his friend and agreed to pay it off in monthly installments over a period of a year, including 5% simple interest. We'd like to know what his monthly payments are. There's the information. He borrowed $3,000 for a period of a year at 5% interest. And this is a little different because we like to know what the monthly payments are that include the principal plus the interest at the end of that year. Summarizing the information, we're given $3,000 paid over a year, 12 equal payments at 5% APR, and we're asked what is each of the individual monthly payments. We have the same kind of diagram. There was the $3,000, and there's the final balance, and that's got to be divided over equivalent monthly payments. There's what we have. The final balance is the principal plus the interest, and if we then calculate what the interest is first, the interest is the principal times the rate times the time. If I put that in, I find that the interest then is $3,000 times 0.05, which is the APR, times a period of 1 year. If I work this out, I find the interest is $150. But then I'm not done yet. The balance, the final balance, is the principal plus the interest. If I work that out, that's $3,150 total that I should return to my friend at the end of the year. What should I pay in monthly payments in order to accomplish this? I need to divide that by 12, and when I do, I find I need to make 12 monthly payments of $262.50. Let's look at another example. And here is an example of compound interest. Rosa deposits $200 each month for 3 months into an account that pays 6% APR compounded monthly. How much does she have at the end of 3 months in the account? And then deposits and compounding occur at the end of the month. Here's the info. $200 a month for 3 months. At the beginning of each month, she makes a $200 deposit, and that's interest at 6% APR compounded at the end of each month. We'd like to know how much she has left at the end of, how much she has accumulated, I should say, at the end of those 3 months. Summarizing, $200 a month, 6% yearly interest, 3 months compounded monthly. What I'd like to know is, what has she accumulated at the end of the 3 months? And the best way to talk about this is with a table, because remember, at the beginning of every month, she takes what is in the bank and then adds another $200 to it. So it's not like that $600 is in there to start with. It comes in at the beginning of each of the months. So what we need to do is calculate what the ending balance is at the end of each of the months, add that to add that to $200 at the beginning of the next month. And what we want to know is how much we have at the end of the 3 months. The first thing we'll do is find A. We start with $200, and there's the formula for the total balance for the compound interest. And there's a table that will help us. In this case, we want to have only one iteration, because T is the end of a month, and since we're given yearly interest, T for 1 month is 1/12 of a year, but we're only interested in what is the final balance at the end of 1 month. So we're only doing one iteration. So N here, you don't have to get your calculators out for that, that's equal to 1. Doing the calculation, putting the numbers in, this will find out what we have at the end of the first month. When we work this out, it's 200 times 1.005, or $201. Let's update the table. So at the end of the first month, we have $201. We put in another 200. At the beginning of the second month, we have $401. There's the table. We work the problem exactly the same way, now with 401 as the new principal starting this off. When we do the math here, we find out, and I'm going to keep the decimal places here for accuracy. Normally, I would round this off to $403.01, but let's keep the whole thing. Here's what we have at the end of the second month. Now at the beginning of the third month, what we have is $603. We do the same thing with the $603, do the math, and finally it looks like we have $606.02. Starting with the $600 that we put in total, it looks very much like we've made over the 3 months interest of $6.02.